This rotating shape shows exactly what trigonometry is designed to do. It calculates how an angle translates into exact horizontal and vertical movement using three core functions: sine, cosine, and tangent. Before calculating anything, we have to define the angle itself. In algebra, we use the letter x to hold the place of an unknown number. In trigonometry, we use the Greek letter theta to hold the place of a specific angle, like 30 degrees. We analyze that angle by looking at the right triangle it creates. There are three key sides to identify. The first is the hypotenuse. It is always the longest side, and you will always find it directly opposite the square 90-degree corner. The other two sides are named based on where theta is located. The side directly across from your angle is the opposite side. The side resting right next to your angle is the adjacent side. If your reference angle moves to a different corner, the opposite and adjacent sides must move with it. They swap positions based entirely on where theta sits. Locking in these relative definitions is your first priority. Every calculation from this point forward relies on accurately identifying which side is which. To connect your angle to those side lengths, we use a standard memory tool, SOHCAHTOA. Sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, tangent equals opposite over adjacent. We can apply those rules directly to a standard triangle with side lengths of 3, 4, and a hypotenuse of 5. Following SO, the sine of our angle is the opposite side divided by the hypotenuse, 3 divided by 5, which equals 0.6. Following CA, the cosine is the adjacent side over the hypotenuse, 4 divided by 5, or 0.8. Finally, following TOA, the tangent is the opposite over the adjacent, 3 divided by 4, giving us 0.75. Look closely at those results. If you take your sine value of 0.6 and divide it by your cosine value of 0.8, you get exactly 0.75. Tangent is simply the sine divided by the cosine. We can scale this logic up by pinning our triangle to the center of a graph. When we spin the triangle, the hypotenuse becomes the constant radius of a circle. This gives us our two master formulas for mapping points. Cosine controls horizontal movement along the x-axis. Sine controls vertical movement along the y-axis. Multiply your radius by those values, and you get exact coordinates. If we have a radius of 10 pointing at a 30-degree angle, we find the x-coordinate by taking 10 times the cosine of 30. That is 10 times 0.866, placing our horizontal position at 8.66. We find the y-coordinate by taking 10 times the sine of 30. 10 times 0.5 equals exactly 5. Our exact location on the grid is 8.66 on the x and 5 on the y. As the radius moves around the circle, the math shifts. If the angle pushes past vertical and points to the left, x moves backward, making the cosine negative. If it drops below the horizontal line, y goes down, making the sine negative. This rotation also explains why tangent eventually breaks. At exactly 90 degrees, horizontal movement hits 0. Because tangent requires dividing sine by cosine, and you cannot divide by 0, the tangent at 90 degrees is mathematically undefined. Mapping these triangle sides to a coordinate grid provides a method for describing any location on a circular path using a radius and an angle. Let's put that to the test. Calculate the exact x and y coordinates for a circle with a radius of 20 parked at 180 degrees. At 180 degrees, the radius is completely flat, pointing strictly to the left. The cosine is -1. 20 times -1 means x is -20. Because the line is perfectly flat, it has 0 height. The sine of 180 is 0. 20 times 0 is 0, making our final coordinate, -20, 0. Internalizing how sine and cosine behave at these four main axes points, 0, 90, 180, and 270, prevents logical errors and saves you immense calculation time later. If you plan to calculate angles in a database or write geometry in code, you have to translate this logic. Computers do not understand human degrees. They calculate using radians. Radians tie the angle directly to the circle's circumference. A full 360-degree rotation maps to 2 pi radians. A half circle is exactly 1 pi radian. To plot coordinates in SQL, nest a conversion function inside your calculation. Convert degrees into radians first, then apply the cosine and sine multipliers. Because SQL and other programming languages expect radians by default, skipping this conversion produces coordinates that do not align with the intended degree values. These relationships are governed by a formula derived from the Pythagorean theorem. On a unit circle, the squared horizontal and vertical values always sum to 1. Take a screenshot of this page right now. This cheat sheet contains the core definitions, the coordinate formulas, and that fundamental identity rule. Before moving on, use those formulas to solve these 3 practice questions. Work through them on paper and check your answers at the bottom. By mastering SOHCAHTOA and how the axes map to cosine and sine, you now have the exact vocabulary required to solve advanced angular problems.